If anyone wants to get up, stretch a little bit, please feel free because it could be tiring to sit for so long. Hello, good evening, everyone. I'm Pranav. I'm an AI engineer at New Jersey Institute of Technology, and I will be speaking about multi-agentic architectures and how we can use multi-agents in order to solve the various problems that we face in production or even in local. So the first and foremost, production reliability crisis. I was shocked to see this graph. This graph actually the max failure rate of multi-agentic systems, not just single agents. So even in multi-agentic systems, around 80% of the multi-agentic systems, they fail when in production. And this research was done by MAST, which was the Berkeley and CMU collaboration. Now, firstly, in order to understand multi-agents, this is what AI agents are. So multi-agents are nothing but collection of AI agents. What are AI agents? AI agents, they are basically artificial agents which are goal directed. So they have a particular goal to target, to complete. They have the access or ability to tool use, and they maintain the memory in a given context state. So why do single agents fail at scale? Not just at scale, single agents also fail in local. So number one, we have context overflow, and some time before someone talked about context rot. So that's another reason that single agents or multi agents also fail. There is hard coded routing, there is cascading failures, or we try to generalize one particular agent for every single thing. Agents don't work well when we give it too many tasks to do. They tend to hallucinate a lot. So in order to tackle that, I would recommend give small chunks of challenge to multiple agents working in unison or in multiple different orchestrations. Today, I will be discussing some of the orchestrations that I have personally explored. So A2A orchestration, agent-to-agent orchestration, agent-to-agent interactions was initially introduced by Google last year. I think it was in May 2025. So it was soon after MCP was hot in the market. And so agent-to-agent orchestration works this way. So there is an orchestrator which delegates the work to specialist agents, and then we could have a critic or a judge, LLM as a judge, or we can have an RLAI so reinforcement learning with reinforcement learning from AI's response. RLHF is reinforced learning with human feedback. RLAIF is reinforcement learning with AI's feedback. This was a new concept brought out in the market in 2023, RLAIF. And then sometime last year, there was a new concept called RLVR, reinforcement learning with verifiable rewards. Verifiable rewards could be the rewards. So in this particular case, we can use this critic or judge as an RLVR model where the judge, it compares the results of this particular orchestration with the knowledge base, with whatever we have in the company's base or with whatever is available online in real time. So those are the initial inputs along with the results and gives a reward score to the entire orchestration. And that way we can make the orchestration improve with every single prompt or command. So these are the 12 patterns that I plan on discussing today. We have foundational patterns, we have some advanced patterns, and the most emerging patterns are the black box patterns and multi-agent swarms. And don't worry about taking the photos. They are already available on my GitHub, and I will be sharing a link towards the end. So pattern one, sequential. In sequential pattern, we have a bunch of agents working sequentially. No matter what, agent A is always called first, agent B is called next, and so on. It's a sequential pattern. There's no complication involved. So that's the simplest pattern. So one of the examples could be, let's take a job application example. I am a job seeker, and so I have been exploring in this field for a while. Job application pattern. So it could be sequential. Number one, I give job description. Number two, agent creates resume. Number 3, agent B creates cover letter. Agent C, it does the company sentimental analysis. Things like that. It's a recurring loop. So it does not do anything new. So that's the simplest pattern possible. Next is hierarchical pattern. In hierarchical pattern, we have a particular orchestrator, a single orchestrator, which delegates the work to the specialist agent. We have a bunch of specialist agents, and orchestrator decides which agent to pass on the work to. And the specialist agent responds with the output. So this is a simple orchestrator design. This is pattern 3, collaborative. In collaborative pattern, 2 or more agents can collaborate with each other to get to a simple goal. So in this particular case, in decision gate, this is an RLVR style model. So decision gate could compare with the knowledge base and send it back, or give the final output. Pattern 4, competitive. You guys might have seen the LLM Council, which was vibe coded by Mr. Andre last year. I don't remember his full name, but it was vibe coded by him, and it was pretty famous last year. And in LLM Council, there are a bunch of agents. All the agents are given that task. And then the response of each agent is scored by every other agent. And then the best scored agent is chosen. That's the LLM Council model. So this is one of the examples of competitive architecture. Then number 5, we can have event-driven patterns. Let's say I connect my agent to GitHub in real time. There's a production failure. A log is generated, it triggers, the event bus is triggered, and accordingly the bots are called. So that is event-driven multi-agentic orchestration. Pattern 6, another fairly simpler model. It's fan-out, fan-in. So in this particular case, we have input, which is split between multiple agents. So multiple agents here, because if you give too many tasks to a single agent, it hallucinates. So you delegate the task to different agents. Then get it in a single place. It's basically very similar to sequential, but in this case, we have only, this is one sequential pattern, this is one sequential pattern, this is one sequential pattern. Here, the task is divided. That's the only difference. Number 7, we can have hybrid routing. Now, hybrid routing is especially helpful when cost could be a huge deciding factor, or when speed also matters. Whenever we make LLM calls, there is a latency involved, a particular latency involved. And in multi-agents, the latency increases with each agent. We can delegate the work to simple agents whenever much smarter decision making is not involved. So we can go with premium agents only when we need to do a complex task. For example, a complex task example could be code review complete end-to-end is a complex task that cannot be done by a local agent. It needs to be done by a smart reasoning agent for better results. So in that case, I can use the cloud models, or in most cases, I can use local LLMs, or I can also have traditional machine learning or deep learning based agents set up, so that if I have traditional machine learning or deep learning based agents, then there's latency. The latency involved is much less because the agents will be much faster. We do not tokenize. So as we learned a while back, LLMs are token hungry. So if we eliminate so I recommend eliminate LLMs wherever possible and involve simple agents rather than using LLMs everywhere. So that reduces cost. Using simple agents reduces costs, increases speed, and increases reliability, because the agents, those simple agents never assume. They always get data from the knowledge base only. Next one is RLVR style feedback. So that's the one I covered a while back. So we have the knowledge base, we compare, and we keep regenerating the response based on the knowledge base. Or in RLVR style, so there's one more thing. LLMs tend to hallucinate a lot, because whenever LLMs say something like, I don't know, they get a lower reward score. These are reinforcement learning models. So whenever they say something like, I don't know, they get a much lower reward score. LLMs try to get as high of a reward score as possible, and hence they tend to assume a lot of things. So in order to reduce that, we could have an RLVR style model which penalizes the single agent or multi-agents whenever it assumes something which is not relevant from the knowledge base. And that's an RLVR style feedback. So we can have adversarial debate. So we can have a pro agent and a con agent. So pro agent says the pros, or so it's basically a straightforward multi-agentic system. So we have so the pro agent and the con agent, they bring forth their opinions, and then we have a judge agent. So it could be LLM as a judge, it could be RLVR style judge. So it could be anything based on our use case. And then the judge agent decides which one did better and gives that output. If everyone could scan this particular code, this is an actor critic agent. So it's a live demo. In this particular case, you give a task to it's a basically chat interaction between an actor and a critic. So whenever you give a task, the actor will implement the task, the critic will criticize the actor's task. Then the actor again improves on the task based on the critic's response. So here, this is also an implementation of LLM as a judge. But this is a live demo. You can try using it, and you do not have to do anything. You can just chat with it and try it out. Yeah, just a sec. Yeah. No problem. Number one, this is one of the experimental agents. This one and the next one is among the experimental agents. So pattern 11 is Blackboard. So in Blackboard, all the agents work around a single shared goal, but whatever the agents do is always stored in the Blackboard. In the Blackboard, we have a design first and then implementation. And after each implementation, the implementation is recorded here. So in this particular case, all these agents, they never talk to each other directly. All the interaction happens through this Blackboard only. So that's one of the differences. So this is one of the experimental pattern that I have explored around. And the last one would be pattern 12, agent swarms, where all agents interact with each other towards completing the shared goal. This is the implementation that is currently done in Cursor, currently done in Claude Code or WAP. So they use multi-agentic swarms to complete a particular to get to a particular shared goal. These are just some of the tips for how to choose the decision matrix or how to choose a given pattern. If you have issues with hallucinations, if you have logical errors, you can use actor critic or adversarial debate models because their primary concern is quality. So if you have context window overflow, for example, then you can just delegate it to a fan-out, fan-in agent so that your entire context window is split into multiple subcontexts. So that way, each agent does a small job and everything is consolidated later on once the job is done. So similarly, there are other patterns. All of it will be available on my slides, and my slides will be available for you to download. Now, anti-patterns to not follow. So when you try doing a God orchestrator, a particular orchestration to do everything, it's going to fail. It's going to hallucinate. It will not be able to perform, and it will be slowing down a lot down the line. A God orchestrator, at least right now, is a no-no. Again, yeah, this is important. Infinite loops, never get into it. So when we are working with multi-agentic orchestrations, we tend to forget closing the infinite loop. Always have a safe command like max turn equals 10 here. Always have a particular cap on how many times each agent can be called. Otherwise, it can go into infinite loop, and agents like doing that a lot. There are just a few more. So resume-driven development, that's basically knowledge-based driven development. I'll correct that. And context pollution. Again, if your context is polluted, if it is not good, then your multi-agents are not going to perform. These are some of the key takeaways. So architecture is more important than just blind prompting. What I tend to do is I tend to decide on an architecture. Whenever whenever I try solving a problem, I first decide on an architecture, and only once the architecture is decided, I start developing the solution and start sequential, then keep on evolving. And that's why keep your architecture open to evolution. And yes, log everything. That's also important. Every single thing need to be logged for your own reference. Yeah, that's about it. If you scan the QR code, it will take you to my portfolio. The presentation is already on my portfolio in the project section, I think. And you can connect with me on LinkedIn. You can look at what I'm developing on my GitHub. Everything is connected to my portfolio. Again, you can just scan the QR code. Yeah. And here are some of the further reading recommendations that I found to be good sources. Yeah. Thank you. Any questions?
Concurrently, would there be a concept of just stop and the first station solve the problem, or would they keep going and all find the same solution?
That would not happen because in the swarm agents, the agents interact with each other as well. And so the agents know what other agents are working towards. That way, in swarm agents, we always have a safeguard saying if another agent is working on it, do not work on that yourself.
Great.
Yeah. Okay, it's multi-agent architectures.ppt. You need to download it. It's not visible on GitHub because GitHub cannot just show the PPTs.
Okay, a question regarding multi-agentic failures. Those 87 or something %, can you break it down into maybe reasons for those failures? And maybe if you speak about those patterns, 11 patterns you presented, which of them might have a higher chance of failure than others?
That could be a long talk. We can talk on, but
okay.
Mostly the thing that I have seen is multi-agents fail because number one, infinite loops. Number two, the prompting is not very clear. And so it's when the prompting is a little vague and when the architecture is not well defined, the user is not satisfied with the results. And that's why we keep failing, because there are things that are broken, but we are unable to tell the multi-agentic system what to do because they are not defined before. But yeah, about that particular study, you might have to read through that entire paper to understand more. And we can connect about that one study was last year, and we can connect and speak about it later on. Yeah.
Okay, I think that's
Yeah.
all. Thank you.
Thank you.